Now that you know what sharding is all about, let's take a look at something different, although related, namely replication. When we talked about sharding, you learned that an index consists of a single shard by default. But what happens if the node where a shard is stored breaks down, i.e. has a disk failure? The answer is simple: the data is lost, since we have no copy of it. That's obviously a major problem, as hardware can fail at any given time. The more hard drives that are used to run your cluster, the higher the chances of a failure. Obviously, this needs to be dealt with, because we want to be able to sleep at night, knowing that a hard drive failure is not a disaster. Therefore, we need some fault tolerance and failover mechanism, which is where replication comes into the picture. Elasticsearch natively supports replication of shards, and this is actually enabled by default with zero configuration. How cool is that? Many databases also have replication functionality, but setting it up can be quite complicated, so getting all of this for free is really awesome. So how does replication work in Elasticsearch? As you know, an index is configured to store its data within a number of shards, which may be stored across multiple nodes. Likewise, replication is also configured at the index level. Replication works by creating copies of each of the shards that an index contains. These copies are referred to as replicas or replica shards. A shard that has been replicated one or more times is referred to as a primary shard. A primary shard and its replica shards are referred to as a replication group. Replica shards are a complete copy of a shard that can serve search requests, just like the primary shard. When creating an index, we can choose how many replicas of each shard that we want, with 1 being the default value. So, an index contains shards, which in turn may contain replica shards. In the example diagram that you see on your screen, an index has been split into 2 primary shards, each having 2 replica shards. The index therefore contains 2 replication groups. Great, so we have physical copies of each of our shards, but how does that help if the entire disk stops working and we lose all of its data? To prevent this from happening, replica shards are never stored on the same node as their primary shard. This means that if one node disappears, there will always be at least 1 copy of a shard's data available on a different node. How many copies will be left depends on how many replicas are configured for the index and how many nodes the cluster contains. On the diagram, you can see that the replica shards are placed on a different node than the primary shard they belong to. Replication only makes sense for clusters that contain more than 1 node, because otherwise replication is not going to help if the only available node breaks down. For this reason, Elasticsearch will only add replica shards for clusters with multiple nodes. You can still configure an index to contain 1 or more replicas for each shard, but it will not have any effect until an additional node is added. Let's go through an example of how replication works within an Elasticsearch cluster. To keep things simple, let's say that we only have 2 indices within the cluster, and that both indices use the default configuration. We start out with a cluster consisting of a single node. Each index contains only 1 shard, so the node will contain a total of 2 shards. Even though the indices are configured to replicate each shard once, the replica shards will be unassigned because we only have a single node running. This is fine for a development environment because it's only inconvenient if we lose data. However, for a production environment, we really don't want to risk losing any data, so we decide to add an additional node to the cluster. Remember that these nodes don't need to be powerful at all. They just need to run on independent hardware so that there's no single point of failure. Once Elasticsearch recognizes that we have added an additional node, it will enable replication, meaning that the replica shards will be assigned. Had we configured the indices to replicate shards twice, 2 replica shards would be placed on the other node instead, but the concept remains the same. If we would then add an additional node to the cluster, we would see that the replica shards would be spread out to increase the availability even more. In that case, we wouldn't lose any data even if 2 nodes went down at the same time. Typically, you would be fine with 1 or 2 replicas, but that depends on how critical your setup is. If 2 nodes break down at the same time, can you then restore the data that was stored on them from another data source, such as a relational database? And is it even acceptable for the data to be unavailable while you restore it? If you're using Elasticsearch for powering the search functionality on your personal WordPress blog, you would probably be fine with this very small risk. On the other hand, if you're using Elasticsearch for something critical within a hospital, you probably cannot afford to take that risk. As a rule of thumb, you should replicate shards once, and for critical systems, you should replicate them twice or more. This also means that for a production setup, you will need at least 2 nodes to protect yourself against data loss. While we are talking about preventing data loss, I want to briefly mention that Elasticsearch also supports taking snapshots, just like many databases do. Snapshots provide a way to take backups so that you can restore data to a point in time. You can either snapshot specific indices or the entire cluster. So, if we can take snapshots, why do we need replication? Replication is indeed a way of preventing data loss, but replication only works with live data. This essentially means that replication ensures that you won't lose the data that a given index stores at the current point in time. Snapshots, on the other hand, enable you to export the current state of the cluster or specific indices to a file. This file can then be used to restore the state of the cluster or indices to that state. For instance, imagine that we have been tasked to restructure how millions of documents are stored within an index. Of course, we think that it's going to work, and we have tested it on our development machine. To be sure that we can recover from any implications, we snapshot the index before running the queries. When running the queries, things didn't go as planned, perhaps because our test documents differed from the documents stored within the live index. Whatever the cause, the documents got messed up, and we need to revert the changes to get things back to a working state. Replication cannot help with that, because replication just ensures that we don't lose our latest data, which has already been modified in this example. Instead, we need to revert the state of the index to the snapshot that we took. Doing that, we should be all good and ready to try again, after having fixed whatever went wrong. So hopefully you understand the difference between snapshots and replication. Snapshots are commonly used for daily backups, and manual snapshots may be taken before applying changes to data, just to make sure that there is a way to roll back the changes in case something goes wrong. Replication just ensures that indices can recover from a node failure and keep serving requests as if nothing had happened. Replication actually serves a secondary purpose as well. Apart from preventing data loss, it can be used to increase the throughput of a given index. Suppose that we have a web shop where we have the products stored within an index named products. We display the most popular products on the front page, and we also run queries against the index when users search for products. Needless to say, this index gets queried a lot. The index is configured to only have 1 shard, because we don't have that many documents. We just run a lot of queries against the index. The replica count is also set to just 1. We're starting to experience a performance bottleneck for the queries run against the index at peak hours, so we need to find a way to handle that. The initial thought could be to add an additional node to the cluster, which, by the way, currently consists of 2 nodes. Having only a primary shard and one replica shard, that's not going to help, because we cannot spread these out across more than 2 nodes anyway. For us to utilize the additional node, we would have to increase the number of shards, or the number of replica shards. We don't really need another node, and we also don't want to increase our costs. Instead, we can increase the number of replica shards by 1, or however many we need. Since we only have 2 nodes, we're not really increasing the availability of the index, but we are increasing the throughput of the index. But how? Remember how I told you that a replica shard is a fully functional index on its own, just like a shard is. This actually means that both of the replica shards can be queried at the same time. This is possible because of 2 things. The fact that Elasticsearch automatically coordinates where queries will be executed, and parallelization. Elasticsearch will automatically select the shard that will execute a given query, based on a number of factors that we'll get back to later in the course. This means that if we have 3 search requests coming in at the same time, they can be executed on 3 different shards, the primary shard and both of the replica shards. So in that case, we can have 3 queries running at the same time, searching the same index. But how is that possible when we only have 2 nodes, you might wonder? That's possible because any CPU that's less than a decade old has multiple cores, typically at least 4. This enables the CPU to run tasks simultaneously on each of the cores by using threads. In this example, this means that the node hosting the 2 replica shards can run a search query on each of the shards in parallel, thus increasing the throughput of the index. Of course, adding more replica shards will only be beneficial in terms of performance if the hardware resources of the node have not yet been fully utilized. That's the case in our example, since the load is unevenly distributed across our indices. If the nodes were already busy handling requests for other indices, we would see little to no effect of adding an additional replica shard. On top of that, we also need additional disk space to store the replica shard, since it's a full copy of the primary shard. As I'm sure you can see by now, there are a lot of variables that affect how many nodes, shards and replica shards are optimal. This was just an example of how replication can be used to increase the throughput of an index. So, to summarize, replication serves 2 purposes: increasing availability and throughput of an index. Let's head over to Kibana for a moment, because I want to show you something. First up, let's actually create a new index. That's super easy. We just specify the put HTTP verb, followed by the name of the index we want to create. I'll just give it a name of pages. Great, our index has now been created. Since we didn't specify any settings, it was created using the default settings, being 1 primary shard and 1 replica shard. Let's inspect the cluster again. For that, I've prepared 2 queries that you've seen before, so let's begin by checking the cluster's health. Notice how the cluster's health has changed from green to yellow, so what's up with that? Let's list the indices that our cluster contains for clues. Here we can see that the status of our newly created index is set to yellow. The reason for that is that the index contains a replica shard, but that shard is not allocated to any node. You already know the cause of that, being that a replica shard is never allocated to the same node as its primary shard. And since our cluster only contains a single node, Elasticsearch has nowhere to allocate the replica shard to. The replica shard is therefore pending to be allocated, which will happen if we add an additional node. So that's the reason our cluster and index is in a yellow state. The index is fully functional, but we're at the risk of data loss in case the node goes down, so the yellow state is a warning for that. Let's now list all of the shards within our cluster and see where they have been allocated. For that, we can use the _cat API and its shards command. So get _cat and shards, and I'll just make the output verbose. The results show a list of each shard along with various information about it, including which index it belongs to. At the top, we can see 2 shards for our newly created index, with one being the primary shard and one being the replica shard. This is specified within the pri_rep column, where P corresponds to primary shard and R corresponds to replica shard. The next column specifies the state of the shard. As we can see, the primary shard has a state of started, meaning that it's fully functional and available for requests. The replica shard, on the other hand, has a state of unassigned, which is because we need to add another node to the cluster for replication to have any effects. Now that you know the reason our cluster is in a yellow state, let's review the list of indices once again, because I want to show you one last thing. Did you notice that the Kibana indices are configured with 1 shard and 0 replicas? The 1 shard makes sense because these indices will be storing very small amounts of data, and the query throughput will be limited. But doesn't having no replica shards put us at risk of losing data? Yes, indeed it does. Don't be fooled by these zeros though, because if we were to add another node to the cluster, these zeros would increase to 1. How? Because the Kibana indices are configured with a setting named auto expand replicas with a value of 0 to 1. What this setting does is to dynamically change the number of replicas depending on how many nodes our cluster contains. When we only have a single node, there will be 0 replicas, and for more than one node, there will be 1 replica. You will see this in action soon, so I just wanted to point it out now in case you were wondering. That's the end of this lecture. You should now have a decent understanding of how replication works in Elasticsearch and the purpose of having replica shards.